Now, for some reason, I've given myself a rod for my own back, in the sense that every now and then I try to swear I'm not going to do another talk that has numbers in it, because that always binds you. If you run over time, you can't just drop the last one and nobody knows. I'm giving you 6 here, so yeah, it's kind of 6. So 6 impossible things, and the quote there is taken from Alice in Wonderland, actually Through the Looking Glass, and what Alice found there. Sometimes I believed as many as 6 impossible things before breakfast. This is what the White Queen says. Again, I don't know whether this is before breakfast for you. It might be, and that might be because of time zone, or it might just be because you run a slightly different personal time zone. You know, all-day breakfast is a thing. And what I want to talk about is not so much the possibilities, but the boundaries of what we can know and what we can do. And these are realistic boundaries. These are boundaries that are set by the universe, in essence. So let's start off. In one sense, they're all interrelated, and so in one sense, I could say it's just boundaries of knowledge. That's one thing. But let me be more specific. Let's do this as a countdown. First of all, representations can be infinite. Now, just an additional thing I've just noticed. Dave Steffen's just made an observation. Yes, I've got a chat window up. It doesn't mean I'm monitoring it perfectly because I'm constrained by substandard human vision. But I will try and pay attention. I've got a Q&A window up. I've got the chat window up. Somewhere behind multiple layers, I have a Discord window up, and so I won't be responding to that just yet. I might get around to it afterwards, and then I will be in Gathertown afterwards. So representations can be infinite. This is an impossibility. Now, of course, there are things that we can talk about. We can say, hey, look, I've got an IEEE 754 representation for floating point numbers. I can say I can talk about infinity at each end of the number line. But that's not actually an infinite representation. That's just talking about it without it actually being it. And then there are other non-finites. Perhaps the most popular one is nan. This is the difficulty that people run into, and I'm sure that everybody's had this experience, that online experience, that in your app experience, in your browser experience, on your phone experience, where you are cheerfully but completely informed that something is nan. And here we have a glorious truism from Lufthansa that nan is not a number. Yes, we know, thank you. But sometimes it's slightly more severe than that. This is one from last year. Driverless race car drives straight into a wall. We keep hearing about the driverless car revolution and all the rest of it. Yeah, just keep your hands on the wheel for the minute. This is to do with the racing. This is to do with basically autonomous vehicle racing, and this is to do with poor state management. During the initialization lap, something happened which apparently caused the steering control signal to go to nan. So in other words, some interesting sticky state and a failure to model the state possibilities of a system. That's probably one of the most common things I encounter. People don't have a good grasp of the state possibilities of a system. They're always thinking just in terms of the code rather than in terms of how another angle or perspective on their code. And subsequently, the steering wheel locked to a maximum value to the right, so it slammed straight into the wall. What was interesting about this is that when this became news, and I retweeted it last year, I had somebody going, what, you mean they wrote it in JavaScript? People have come to think of nan as being associated with JavaScript. That's certainly its most popular source these days, but it dates back to the IEEE 754, which is the late 80s. And I've experienced nan in a number of environments. It turns out actually in this particular case, the code was written in Mathematica for the car. But it is sufficiently popular that I'm kind of wondering that there's kind of a soundtrack here. We should perhaps call these Batman bugs. A good suggestion, after having done 6 impossible things, I should have breakfast at Milliway's. For those of you that don't get the reference, I do actually have a Douglas Adams reference a little bit later on. So that's nicely preempted there. So let's talk about some things, and things with numbers. Here's that. 97 Things Every Programmer Should Know, which was published 11 years ago. And I managed to get Chuck Allison, who used to be involved in C++ Standards Committee and a number of other related things. Floating point numbers aren't real. Interestingly enough, this is actually the piece that triggered me to propose editing this book. It was a frustration one summer, would have been the summer of 2009, I guess, maybe, that I was really frustrated. I'd seen a piece of code and it was one of those standard floating point errors. And I just said, it's just one of those things that programmers should know. And I thought, wait a minute. So I had a title, and I just knew that Chuck had already written a whole load of stuff on 754 representations. I said, could you contribute something under this title? So the point here, floating point numbers are real. Real numbers have infinite precision, and therefore continuous and non-lossy. Floating point numbers have limited precision, so they are finite, and they resemble badly behaved integers. I love this description. It is one of the most perfect descriptions. It's not simply that they are bounded, it's that they are, it's not simply they're like integers, it's they're badly behaved integers. They're the integers that you just don't take home to meet your parents, okay? But there's an assumption here. There is an assumption here that integers are well behaved. And actually, we experience enough problems. So I'm just going to travel back in time 8 years here. I want you to focus on Visual Studio and my license expiry, which has a suspicious number that if you are a developer, you kind of look at that number. For everybody else, this is an arbitrary number. For anybody involved in development, it's just like, yeah, I know what this is. This is int max. Or, sorry, I've got to be politically correct about this. This is one is standard numeric underscore limits, angle brackets, in angle brackets, colon, colon, max, int max. One thing that C++'s traits have, that you're never going to be accused of being brief and eloquent and to the point with them. So if you're being paid by the character, this is great stuff. So here's a rather suspicious, your license will expire in 2 billion days. But there's clearly some other comparison that is not quite right, because my license has gone stale and must be updated. Honestly, I thought I was good for millennia. It turns out that there are limits, and we have a blind spot. We have this very simple developer, 0, 1, many. Oh, that's quite big. Okay, this is a very simple human thing, 1, 2, 3, many. But that's quite big, and so we start thinking, oh, that'll never get big. The history of software failures is riddled with examples of people going, oh, we'll never get a number that big. Oh, that'll never happen. And then it happens and it becomes a story and somebody quotes it later. What I want to do now is I want to take you back to the late 90s. Just around the time, this was actually around 98, the particular book was published, and I'm not going to name any names, but this is a binary search. This is actually, this binary search works. It's in a published book, but it suffers from a problem. And you might say, well, yeah, sure, let's rearrange the indentation a little bit, a bit more spacing, get the indentation right, 3 spaces. If you're doing 3 spaces, I'm sorry, unfriend. So we've got that, and then there's a couple of other things. We can improve the locality here. Why are we declaring middle up the top? It's not used except in the loop, and all the rest of it. Yeah, these are all cosmetic. That's not actually the issue that I'm highlighting. I want to highlight an issue that was accidentally stumbled upon by John Bentley. In 1983, he wrote in his Programming Pearls column for Communications of the ACM, and a lot of these are collected together. John Bentley's Programming Pearls, then there's more Programming Pearls, and then there's the second edition of this book, which is published in the 1990s, an update. There's still a lot of good gems in here, a lot of nice observations. And in the what we will now discover is the ironically named article, Writing Correct Programs. Now, you have undoubtedly heard of Murphy's Law. Anything that can go wrong will go wrong, or the variant that is used in Interstellar, anything that can happen will happen. But there is also a thing called Murphy's Law. Murphy's Law is the idea of if you try and correct somebody's spelling or grammar on the internet, your correction will itself contain an error of that nature. So what happens when you write an article about writing correct programs? Yeah, so let's play this one out. So back in 1983, he's talking about all of this kind of stuff. He's talking about program correctness and verification. And this is a point in the 80s where some people genuinely believe that formal methods, as conceived of then, there are formal methods, before anybody starts jumping on this one. There are many contributions for methods of maze, but most of those have been commodified. They are not at the level that we are being offered here. But some of the reasoning tools are very, very powerful. The ability to reason about your code, very powerful. And he presents a binary search algorithm. And so here it is in pseudocode. Then he breaks it out and highlights all of the invariants, what must be true at various points, the assertions in essence. Here are all the things that must be true, and then this is provable. He verifies it, and he says one of the major benefits of program verification is that it gives programmers a language in which they can express that understanding that they have of the code. Of course, these techniques are only a small part of writing correct programs. Keeping the code simple is usually the key to correctness. And again, I have to remind everybody, I often have to, that simplicity is one of those things. It is just such an important asset. But nonetheless, this is a piece on program verification. Several professional programmers who are familiar with these techniques have related to me an experience that is too common in my own programming. When they construct a program, the hard parts work the first time, while the bugs are in the easy parts. This is indeed my experience when teaching people to test things. Often people have this sense of concentrating their tests on the hardest thing. Many of the bugs are in the simple cases, the ones that are almost invisible, they're so simple, the ones that are assumed, and we'll kick into assumptions in a moment. Now that particular binary search algorithm found itself in a standard library a couple of decades later by a student of John Bentley, Joshua Block, who wrote the collections and algorithms for Java and JDK 1.2. And here is the binary search algorithm as rendered in Java. And this is all well and good, does the right things, and again we might make some cosmetic suggestions, and this all works really well until you hit very large arrays. There is a problem here. It's a very simple assumption. The low plus the high, binary search, we're chopping through. We're at the high end. Low plus high. Well, wait a minute, if we're really nudging up against int max, where does this take us? Well, this takes us all the way around here, the other end of the number line. And it is this idea of finding it's just a simple idea, the classic fallacy that people have without realizing it. That's an integer, therefore it behaves like an integer. And therefore they treat it like an integer, and they treat it as if they were at school, and they go ahead, yes, of course, integers are infinite and unbounded, with a cardinality of Aleph null, and that's great. So we can just do what we want with them. And they get it wrong. These two statements are mathematically equivalent, and yet when we hit concrete hardware, they are clearly very, very different. This one will actually find the midpoint between low and high under all circumstances. What we see here is the assumption. Right here, there is an assumption that we can just add these two numbers and do an integer division by 2, and that will be fine, because he is thinking mathematically. Oh, sure, he's formalized it into pseudocode, so it's code-ish, but he's still thinking machine independent. Machine independent thinking it's an abstraction. It can be very powerful, but you also need to recognize it has a limit. What we experience here is the challenge of assumptions. Now, assumptions are really interesting pieces of knowledge, because an assumption is basically something you typically don't know you have until you know that you have it. And normally you know that you have it because it is contradicted. Okay, in other words, an assumption is something that you discover by contradiction, not by exploration, not by analysis, but by contradiction. When somebody says something and you go, oh, I had assumed. At that very moment that you say I had assumed, you discover you had an assumption. And you've had this assumption all along, but had you been asked at any point prior, you wouldn't have been able to reveal that knowledge. So I liken it to being kind of Lego bricks. You might know that there are Lego bricks in the dark, and if you've never stepped on a Lego brick barefoot, then it's an experience you ought to try just to really get the physical feel of the metaphor. As I said, hardware makes a difference. The idea is you may know that they're there, but until you actually step on it, you don't know which ones and where exactly they are. So I'm going to go back to that piece of code. And here we see, actually, that's the issue. There's lots of code out there that does this. Now, if we're running C++ 20, we might go, you know what? Midpoint's going to do the right thing for us. and I can do a simple refactoring, solves the problem. On the other hand, if you are running C++20, then you might as well, this is actually equivalent, this particular binary search is actually equivalent to this. But then again, you might as well just use this. So problem solved by unasking it, but nonetheless it takes us on an interesting journey, particularly when we are dealing with legacy code. There are loads of hidden assumptions. The point there is that there was a point at which we used to think that 32-bit addressing was kind of a big deal, and it was big, and that the idea of having data structures of the order of billions of elements seemed inconceivable. And yet nowadays we don't even call that big data. And for anybody thinking that's fine, we've got 64-bit, just watch your assumption wither away at some point. But again, we don't have to do that with anything. We can just come and divide stuff by 0. This is the Yorktown, which has since been decommissioned. In 1998, it experienced quite literally being dead in the water. There was a little bit of a problem. Its whole network, and therefore the whole system, it was running Windows at the time. They'd migrated from Unix, and this was a question decision. And guess what happened? Turns out that a driver, I believe it must have been a driver, because I can't imagine any other divide by 0 is going to take the whole OS down. A little buffer overrun issue occurred, and therefore, you end up with a very interesting challenge. The point there is that these unbounded, these infinite quantities, they're not just big, it's that they are not representable. As the great bard once said, this is the monstrosity in love and indeed in hate, lady, that the will is infinite and the execution is confined. The desire is boundless and the act a slave to limit. There is always that limit, whatever our desire and imagination can do. Concrete hardware means that we never actually deal with the infinite. Interestingly enough, it also means we never deal with undefined behavior, but perhaps that's something we're going to come to in a moment. So let's look at number 5. Every question has an answer. So this is an impossibility. This is not a valid statement, or rather, it's an assumption many people have. And I want to explore that a little bit with our dear friends Facebook, who are not actually known for testing certain things, except their huge emotional contagion experiment back in, when was it, 2014, to find out if you can sway people's moods, positive or negative, by adjusting the balance of their feed, an experiment that they ran on 700,000 people without consent. It turns out the answer is yes, you can manipulate people's emotions quite successfully and quite easily. However, that's not what we're here for. We're not here for the emotional manipulation. We are here for time travel. So I got this message a while back, logging some issue, and I got told 31st of December 1969 was, this is our reply. We're going to tell you the last day of 1969. Yeah, cheers for that. And it's a case like, what caused this error? There's a number of interesting questions here, because, in software you're sitting there going, yeah, that 31st of December 1969, that is suspiciously close to the beginning of time, and quite literally the beginning of time. The C standard, and therefore the C++ standard, doesn't actually define what the epoch is, but it is commonly implemented in terms of what has now become known as the POSIX epoch, or is classically the Unix epoch, which is a particular fixed point in time. So though I'm not sure I've stumbled across any implementations of time that do seconds to any other epochs, but the epoch that we're all familiar with, that's the standard implementation of that. So we might be thinking, you know what, something got set to a 0 somewhere, and that would put it at the beginning of the epoch, okay? Which is still not 1969. If you want to know the epoch, then look around the internet, you'll find it. There's plenty of errors out there. So apparently Intel were busy pushing drivers in the 1st of January 1970. I don't think they were. What allows us to jump back across the boundary, across the decade boundary? If you want to, by the way, if you want to fight, is that actually a decade boundary, 69 to 70? Yes, it is. I'm happy to explain why you're wrong later if you believe otherwise. Date time handling is fascinating. I have a blog on a number of blogs on this particular aspect. What caused this to go back in time? Well, I'm based in the UK. Facebook is not. Or they'd like to tell you they're everywhere, but no, they are based somewhat west of here. Perhaps It is the fact that the natural enemy of the programmer is the time zone, as Daniel Dash pointed out. So therefore, maybe something got shifted west, which would put it into 1969. Okay, that could get us there. That's one possibility. I used to think about that as the main possibility, but actually I realised a while later, you know what, there's another reason this might be the case. You only have to go 1 second back. And what will take us 1 second back? 1 second back, so the kind of volume that you can beat your colleagues around the head with is C99 standard. It's useful as a weapon, and it contains a great deal of stuff. Interesting enough, a lot of rationale. I always found it interesting that in C++ we never bothered with the rationale. It's just like, it is what it is. Take it. We don't have the time for this. Here's an interesting one. -1 is returned if the calendar time is not available. In other words, what is interesting here is that there is no answer to this question. Or rather, when we are asked what is the answer to that question, there isn't one. And unfortunately, because of the way that the API has been structured, we are answering within the noise, the bandwidth that is already dedicated to the actual legitimate answers. So it turns out that 1 second before midnight and, oh my goodness, I have no answer for you, are indistinguishable. Unfortunate. So here's the point. There are many cases under which the time may not be available. People assume that time is just always there, that time is always present. And that's not an assumption that you can actually hold. There are reasons, system-wise, why the time may not be available. There are operating system permission reasons. There are just cases where, hey, the clock is treated as a device. That may not work. There are cases that is finite and possible. And we don't have an answer to that question. And here's my answer to saying I cannot answer you that question. You were expecting a time, but I will offer you something else. Now, you might say, oh, well, we can solve this with other approaches, by using optional, by using exceptions. I'm not worried about whether you can work around it. I'm just saying that here is a consequence of the very fact that this question does not have an answer under certain circumstances, which are beyond our control. So time is a partial function rather than a total function, which is kind of an important distinction. People often assume another assumption that they're always dealing with total functions. So having gone west, let's go east. So this is Arabic for Al-Khwarizmi, who was not in fact Arabic, but it's the Arabicized version of Muhammad ben Musa Al-Khwarizmi's name, and that was a figure in the Persian Empire, although not necessarily Persian, probably from around the Aral Sea, Khwarezma region, as best as we can make out. But in Roman circles was known as algorithmi. That sounds a little more familiar. And that gave us algorithmus in medieval Latin, and in modern English that gives us algorithm. So Al-Khwarizmi was known for the book that gave us algebra, and also this idea of algorithms. These days we have a very specific idea of what an algorithm is, and we dig it out of the dictionary and we go, oh yeah, a process or set of rules to be followed in calculations or other problem-solving operations, especially by a computer. Now, if we're working in C++, we actually have a header called algorithm. The funniest thing is that algorithm the C++ standard doesn't actually specify algorithms. The header is a complete misnomer. It's not that it doesn't contain algorithms, is that it doesn't specify algorithms. We've used the wrong word. I mean, I know naming's hard, but an algorithm is a specification of control flow. And I just simply ask you, what is the algorithm that std sort uses? Now, you might say, oh, well, in common implementation, it uses intro sort. But is that specified? No. All that is specified is the time complexity and the effect. Okay? It is not specified that it cannot use quicksort or that it must use intro sort. It is specified by effect. The algorithm header does not contain specified algorithms. This is one of the great ironies. It's one of those things. A computer scientist should care about this stuff. We've got a load of stuff all bundled together. Yeah, we should have come up with a better name. But there we go. Now, there's another interesting thing. Let's talk about algorithms. We've talked about kind of performance and stuff like that. So let's actually go and look at an algorithm. So I've been writing a few things recently on esoteric sorting algorithms, or esoteric algorithms, which are really not safe for work. Please don't use these at work, unless you're trying to prove a point about something. You know, if your colleague says, yeah, performance, that never matters, that's not a problem, then feel free, go ahead, implement permutation sort. It has factorial time complexity, or OMG. In essence, it is an unoptimized search through the permutations of the input values until it finds the one arrangement that is sorted. It is also, thanks to the C++ standard library, one of the simplest algorithms to write. Here we go. That's pretty horrific. So, I mean, really, that's got to be bad, yeah? I mean, surely there is nothing worse than that. Well, actually, don't be so sure. This is from a draft of an article where I'm exploring the essence of BOGO sort. Some people confuse BOGO sort and permutation sort. I've been tracing the history of that, but these should not be confused. Permutation sort is a well-defined algorithm. We understand its complexity and its boundedness and its behavior. It never revisits the same permutation. That's the whole point. It is a systematic search. BOGO sort is basically, 52 card pickup. And you may repeat, it is entirely possible to repeat the same, there's a low probability of repeating the same sequence again and again. In fact, there's an interesting thing here. If we actually do this properly as in terms of true randomness, so I'm going to actually use, assuming that I actually have some entropy available to me, then what we've got here is a truly random approach, one that is actually not deterministic. And it has a rather interesting property. This might not actually be an algorithm, because an algorithm has a very well-defined sense, and I'm not just complaining about the naming of the include header. One of the things that distinguishes a procedure from an algorithm, algorithms form a subset of procedures. And they are well defined in the sense that they terminate because they have a result. It is not entirely clear that BOGO sort necessarily must terminate. I'm saying the probability that it fails to terminate is, of course, remarkably small. It is hugging zero intimately, but it's not the same as zero. So it's close, but not that close. So there is a finite non-zero probability that this will never terminate. So therefore, technically speaking, it is not, strictly speaking, an algorithm. Now, one of the things we're kind of hinting at, let's talk about correctness. We talked about program proof. Let's talk about testing. This is a classic book. This is the one. Why am I showing you this book? I'm not going to be talking about structured programming today. It's because that's where the quote that people often point out from Dijkstra, program testing can be used to show the presence of bugs, but never to show their absence. There are boundaries to what we can know. And it is one of the things that, interestingly, I was running a workshop recently, and I had exactly this experience where somebody, and one of the things was indeed one of the pieces of homework that I set people. We've been running this over a series of weeks. One of the pieces was a recently discovered sorting algorithm that has quadratic complexity, and you might say, well, why on earth would I want that? So it's technically worse than bubble sort, but it's incredibly easy to write. And so I can't believe it can sort is the name that I tended to use for that. So I got people to write this. I wanted to see them do it in a kind of generic style, and I wanted them to test it. And actually, although here we're talking BOGO sort rather than I can't believe it can sort, the interesting thing that came out of this was that very common oversight, one that I've seen a number of times, actually to do with the sort example as well as related examples, is when people try and test sort, what they do is they go and assert that the result is sorted. Now, it's not that that's not true, it's just that that's not the whole truth. There are lots of sequences that are sorted that are wildly, massively incorrect. So if I take the sequence 314159 and I accidentally, as one client company did many years ago, accidentally and carefully copy the first element over the whole array, which gives us 33333, that is also sorted and will pass the tests, which is unfortunate. Because what you actually meant to say was, and it's a permutation of the originals. Ah, right. So in other words, to truly describe sorting, it's sorted in non-descending order and is a permutation of the original values. Alternatively, you could make your life nice and simple and just say, I actually know the answer to this one. You know, it's 1, 1, 3, 4, 5, 9. Okay, these two are equal. That's a lot easier than just the circumlocution involved in describing the properties. In this case, we can actually nail the concrete in place. That's fine, but this is BOGO sort. We have an interesting question. If this doesn't terminate, it's also broken. So what we need to do is basically set controls for the end of time. There we go. There's another restaurant at the end of the universe reference there, because this is where we're going to go. The end of time. We're going to set a signal. I'm going to assert that if we reach the end of time and we have not terminated, then this is a failure. So how do we do this? I'm going to step outside of the standard a little bit into the POSIX space. End of time. I'm going to assume that that's infinite. Current theories are the universe is expanding at an ever-increasing rate. Therefore, there will be no big crunch. And so therefore, we set the alarm time for the end of the universe. And if indeed the alarm goes off, then the test has failed. Well, you can see there's a slight problem with this. Actually, let's be pragmatic about this. 1 second should probably do the trick. If we reach 1 second, then probably there's a problem. You know, but this is interesting because it doesn't mean the algorithm's broken. In fact, it doesn't mean that it wasn't going to terminate at 1.001 seconds. But this actually does give us an indication of how we solve things like the halting problem, okay, and related problems. It's very easy. Whenever you have something that could potentially run infinitely, you bound it in time and you introduce non-determinisms. You are always guaranteed a result in finite time. It's just non-deterministic what the result is. So you make a trade. So, you know, you trade one uncertainty for another. But that's actually how you solve problems that are related to that. It's called the timeout. That is one of the reasons we have timeouts. People don't tend to think of themselves as, I'm going to add a timeout here to solve the halting problem. But that is one of the solutions. You introduce an element of non-determinism to bound things in time. That's going to come back in a bit. So, a related theme. Another impossible thing. Every truth can be established where it applies. Now, straight out the gate, we can say, yeah, that's not going to work out for you. This is unfortunate. Girdle kind of basically harpooned the kind of the vision that existed at the turn of the last century, Hilbert's program and all the rest. At the end of the 19th century, there was this idea that not everything would be known. In physics, in maths, we would have a bounded and clockwork universe where everything could be calculated. And then a number of things came along that really messed this up. Quantum mechanics being one of them. General relativity, actually, some of the solutions gave us things like black holes. And then in the domain of maths, this kind of blew a huge hole in Bertrand Russell and Alfred North Whitehead's Principia Mathematica that was kind of published in the pre-World War I optimism. And 20 years later, Gödel's incompleteness theorems basically shattered the dream. So for any consistent axiomatic system, there will always be theorems that cannot be proven within that system. And the important thing here is that we might say, well, what's that got to do? This is just number systems. Well, it's to do with any system that has the richness, as it were, of a number system. And as we know, code has exactly that richness and can be represented within itself. That was another point that Gödel did. He basically said we can represent the number system within itself. And that there are issues that we're going to encounter with this. And the most frustrating one is that there are things that are true, but cannot be proven to be so. Things that are false that cannot be proven to be so. And kind of a classic book in this space. I've actually ended up with 2 copies. This is my slightly battered one, which I no longer open because it kind of is falling apart. It is quite old. It dates back to the I got this one in the mid-80s. Fascinating book, still has a lot to teach us, but one of the wonderful observations there is that basically it boils it down. All consistent axiomatic formulations of number theory it turns out, although I make jokes about the fact that programming is not maths, it's not. People who think that programming is mathematics generally cause problems. And I don't mean they're kind of rogue tearaway mavericks. I mean they write pretty crappy code and miss certain obvious aspects which are primarily human, but also strongly hardware related. But that does not mean that I cannot talk about code using mathematics. Originally I had a physics degree. Physics is not maths, it just happens to use a lot of it. The same can be said for an awful lot of computing. But therefore, it means that there's a number of things that are undecidable. What undecidable propositions can I represent here? Well, let's talk about how long a piece of string is. I believe Sean Parent's going to talk about problems with find. I'm going to talk about an even simpler problem with find. I'm going to strip find back to find a particular character. I'm going to strip it so far back that we're going to find one kind of character. I'm going to look for null. So I'm going to knock this back into the C universe. I'm going to look for null, and I'm going to tell you how far null was away from S. Strlen. And so using the implementation, I think I followed the implementation in KNR fairly faithfully, that we've got this, basically we start at 0, we keep on going until we hit the end of the line, continually counting, see basically when do we hit the null character, and keep on incrementing, and then we're done, and this works fine. So then we start saying, well, hang on, let's talk about correctness. Let's talk about what is the precondition to this. Under what circumstances, what must be true for this to execute correctly? Well, S can't be null. That's not defined behavior for this. And we might sit there and think, well, I'm kind of comfortable with that. Except that's not even close to what needs to be true for this to work. What needs to be true is that there needs to exist an n such that S of n is null and that all points between 0 and n are defined. There is a reason this is in grey and uses odd symbols and italics. It's because you can't write this in C. This cannot be written within the system of standard C inside strlen. In other words, within the system of strlen, as defined by standard C, it is not possible to write the precondition for strlen to work. The only way you can do it is by stepping outside the system. And of course, that system itself has other things that cannot be proven true within that system, but must necessarily be so. I can't tell you at this level whether this is whether each execution will be correct. I have to step outside, and at that point, I am able to, by inspection, by flow analysis, and all the rest of it, I am able to demonstrate at that point, oh yes, this is correct, but I cannot do it from inside the system. So that stuff in grey is not something that you can write and can determine. So if we take a well-defined example, be excellent to each other, and then we're going to print out, okay, the string and the length, then this is great. Be excellent to each other takes 26 characters. This is somehow useful information, Bill and Ted wise. Let's try something different. Let's try something that doesn't have enough space. In other words, let's put aside 5 characters, and we'll initialize each one B-O-G-U-S. And actually, a lot of people assume, are not aware in C that actually you can actually shorthand this to that. The null is not, everybody assumes that the double quotes always ends in a null. No, it doesn't. It's a shorthand. And in certain contexts, you can get away with this. So this is actually just a shorthand for what I just showed. I'm not entirely sure whether that's going to be useful to you, but hey, there it is, trivia. Now, what happens when you execute this? Now, some people would say undefined behavior. There is actually, when you run something on a computer, there is no such thing as undefined behavior. Undefined behavior is an artifact of a specification. It is not a thing that actually exists in the real world. In the real world, things always get defined. There is no kind of like, something happens. And one of the things that can happen is this, because, 5 is an odd number, and the chances are that that there's actually more space that's been reserved here, and it's all nulled. That's one of the possibilities. Another possibility is you find yourself heading towards M87, lost in the voids of space. That is another interpretation. Undefined behavior has a manifestation. The problem is that it's not specified what the manifestation is. So there is no such thing as undefined behavior in the real world. That is an artifact of specification, which is, funnily enough, an artifact of exactly what we're talking about here within a system, what we can say about what happens in terms of correctness and behavior of that system. Alternatively, we could try, this one, just undefined pointer value, and who knows where that leads? Well, probably beyond the shadow of the event horizon in M87. Generally, don't do this at work. This is generally not recommended. But there are some practical consequences of this. One of which is some minor points about whether or not the limits of things like pre and post conditions. We're looking at some kind of rather meager pre and post condition facility arriving in C++23. I don't want to say it's as useful as a chocolate teapot, but it's certainly not. If you've read around program proofs and stuff like that, it's kind of quite a long way down below what might be considered actually useful and meaningful. But even if we were to make it more meaningful and useful, you're still going to find that there are things that cannot be expressed, and that is an intrinsic property of the universe. And also society. We find this in terms of systems, and we find this occurring a lot with things like machine learning. This piece by Adrian Collier that I've already quoted, but now I want to give you a bit more context, is he makes a point about how do we demonstrate the fairness of machine learning systems. And there is this idea of demonstrating it from within the system, from the properties of the model itself, or use the data that it is trained on, and so on. There are broader implications. You need information outside the system to demonstrate the fairness within the system. Otherwise, you are living actually behind that event horizon, and you have a very particular sheltered view. So this is something we need to watch out for. There are very practical implications of this, and we often talk about simplification, we often talk about abstraction, but we need to be very, very careful about how we confuse certain things for another. So we've all been experiencing a rather interesting year and a half or so. And one of the more interesting ones, what have you done with your time? Have you learned to cook rye bread? Have you written more code? Have you learnt a new language, natural or programming? You picked up an instrument. There are all of these possibilities. Or have you just binge watched a hell of a lot of those things you said you were going to binge watch and finally had the time for it? All of these are possibilities. An artist in Berlin, Simon Weckert, decided to do something slightly different. Decided to take 99 Android phones, put them in a handcart, and walk around the streets of Berlin. Guess what? Creates a traffic jam. Now, the point here is we have a simple kind of correlation. What Google Maps is doing is it's going, hey, look, there are a lot of Android phones moving very slowly down this particular street. Walking pace is significantly slower than smooth traffic, and there's a lot of them. This looks like a traffic jam, so therefore we will reroute and advise people to route around. And this was a tangible effect. The point here is that one thing has been mistaken for another. You can't actually know, unless you are there, what the traffic jam is. The best you have is a set of devices that might correlate with a traffic jam, but they do not necessarily represent a traffic jam. The whole point here is this is an abstraction. Abstraction removes details. It allows us to reason very effectively, but it also has side effects. So we end up with all of this kind of stuff. And unless somebody's actually observing it, then we don't actually know that there's traffic. Now, this is kind of important because a number of people, we hear a lot in terms of social media and the large companies, they're always talking about engagement. Engagement. We're measuring engagement. Look it up in a dictionary. The dictionary will tell you the state of being engaged. It's a personal thing. It's an emotional involvement or commitment. Companies do not measure engagement because they don't know how, because they can't. They do not measure it. Well, I guess they could turn on the camera, and I guess a few organisations are probably doing that, but let's leave them to one side. They can't measure engagement. All they measure is activity on a website. When people say engagement, you need to remember it's not engagement. I can tell when I look at somebody whether they're engaged or not. All that's happening is people are measuring clicks and shares. And there may be a correlation, but there may not. And this is massively easily gamed. This is no more sophisticated. All of those statistics about web engagement that people are distorting and creating revenue streams for advertising, these are all somebody walking down a road with 99 phones in their cart. And this is all part of the same thing. You cannot demonstrate the truth that you want in the position and the place that you want. This is a very deep kind of concept. As philosopher and psychologist William James said, we must be careful not to confuse data with the abstractions we use to analyse them. Now, another related thing that we need to explore is another impossibility. The future is knowable before it happens. And there's an important point here, because I opened with the idea that, this is all about knowledge. This is all of these things are the limits to our knowledge. But first of all, before we hit the limits, we need to understand, as the late great Grace Hopper said, to me, programming is more than an important practical art. It is also a gigantic undertaking, the foundations of knowledge. This is software development is applied philosophy. You are taking thought stuff and reshaping it. You are quite literally codifying an understanding of how something should work using a formal notation. And there are sociological aspects to that as well. But what you are doing is codifying knowledge. You're also, as it were, codifying assumption. But you don't know that. So we need to have a decent framework for our knowledge. How do we organise the things that we know? Well, let's start off with the known knowns. Things that I know. Then there's the known unknowns, things that I know I don't know. Now, a lot of people tend to estimate in this particular space. In fact, people tend to estimate based on what they know, plus a little bit of optimism. When it comes to the things they know they don't know, the optimism goes up. But also there's another interesting effect. The importance they place on the things that they do not know is reduced. If I take two things, here's a thing you know and a thing you don't know, how do you rank them? Well, the thing you don't know is not as important as the thing that you know, because if it were important, you'd know it, right? There's this beautiful self-serving cycle that goes on in your brain. It's a great bias, but if you know you don't know something, you say, well, it's not important because otherwise I would know it. So you're already downvoting it, which means you're more likely to be optimistic about it or underestimate its difficulty. But as you notice, I've only got two things here, and there seems to be an awful lot more space on the screen. The unknown unknowns, Donald Rumsfeld's only contribution to, well, anything from what I can tell that was useful. The idea of what about the things we don't know that we don't know? We don't even begin to account for them. If we like, the known knowns are the things that we see immediately around us. The known unknowns are the things towards the horizon. They seem a little bit diminished, but I can still see them. And in case anybody wants to talk about, well, what about the unknown knowns? Actually, it's commutative, so that's already handled. The unknown unknowns, if you like, are the things that are beyond the horizon. Okay, in other words, we don't even know, we cannot even perceive them at that level. Now, this somewhat encourages us to the idea, and this is where our assumptions live, or a lot of our assumptions. Okay, the idea that these are the surprises that typically come up. Now, one of the ways we can develop this is, or deal with this, is to develop continuously. In other words, rather than having these, big upfront design kind of approaches and say, right, we're going to design everything, and there's a whole point here is that if you want to find out what it's like to walk somewhere, then you need to walk somewhere. You can look at all the maps that you want, but until you're walking there, you don't actually know what it's like. We kind of dealt with that in the previous item. Yeah, you've got to be there. And then you can see, isn't that guy walking around with just 99 of these things in the back of his car? The point there is you want to find out what it's like to develop software for that system. You've got to be in that system. You can theorize about it all you want, and that may give you some knowledge, but that tops out really quickly. You've actually got to do this. You've got to put yourself in a position where you're going to stumble across those Lego bricks. You can stand at the door and theorize about it, but until you're actually treading on them, you're not really doing the real work. In other words, this is what Dan Terhorst North refers to as deliberate discovery. I'm going to put myself in a situation where I'm likely to screw up, and I'm going to find things. And it's not the most effective search algorithm. It is probably a little more effective than permutation sort, but it's the same principle. You are wandering through a set of possibilities. But we're not done yet. If you look at the spacing on the slide, there's one more. Technically, there's actually two more. This comes from Philip Armour's, or my rebranding or reframing of Philip Armour's 5 orders of ignorance, which he starts appropriately enough at 0. What you see on screen is 0, 1 and 2. We're about to look at 3. Just to let you know, level 4 or order 4 of ignorance is you don't know the 5 orders of ignorance. Well, we're kind of solving that one here. What's the next one? Unknowable unknowns. The idea of I don't have a process to find out what it is that I don't know until it happens, at which point, and this is an important thing, this is where the future is. Until it happens, we do not have a process for finding out that it has happened. There is no other way of experiencing it than experiencing. There's nothing we can do to preempt. Yeah, this covers things like the halting problem and indeed the rest of the future. Now, what I love about this one, prediction is very difficult, especially about the future. I put Niels Bohr in there, but with a question mark. We don't actually know who said it, and this is the past. So if we can't even tell who said this, the number of people have been attributed, but we don't know definitively who said it in the past, how on earth are we going to deal with the future? This is importantly, and actually somebody's made, Phil has made a really good observation that this is the chaos domain in the chaotic domain in Kevlin. If you've not, so first of all, if you're not familiar with Kevlin or even how to pronounce the word that you've just seen in the chat, Cynefin, it's Kevlin. It's a Welsh word. No, I don't really speak Welsh. Well, Wales is indeed across the water from me where I live, but it is really a way of understanding complex adaptive systems, and it has different domains that range from simple, which is highly ordered, through to chaotic. And there is indeed an interstitial domain that is utterly disordered and is the common lay understanding of the term chaotic, as opposed to the complex adaptive system understanding of the term. The point here is we are dealing with the future, and this takes us into the realms of estimation. I mean, there are some things that we can sometimes say when it comes to estimating, and I love this one from Work Chronicles. What's the estimate a month? What if we add one more engineer, then 2 months? What if we add a project manager? Trust me, you don't want to know. There are some certainties, and this kind of feeds in the cone of uncertainty that Javier was commenting there. One of my favourite stories about estimates going the wrong way was a talk by Tom DeMarco a number of years ago, where he talked about a particular, I think he was quoting a British government project. We have a lot of government projects that go kind of really badly. We're currently in the middle of half a dozen at the moment, it feels like. But this was one a couple of decades back, and they had originally quoted a very, very precise figure for its cost. How much it would cost. I mean, it was one of those curiously precise figures. It was around the £10 million mark, and it was quoted to, I think, 8 or 9 significant figures. In other words, it actually went down to the pennies. It was a very, very precise number. By the time the project had finished and overrun by an order of magnitude, they weren't even able to say how much it had cost them. So in other words, they started with a highly certain figure, about this much, and ended up with something that was around 10 times large, but nobody could say actually what had happened. This feels relevant and appropriate. But this is an important point, as Christopher's observed, precision versus accuracy, hugely, hugely important. But we live in an age of precision. People love precision. They don't even know they love precision. They will read off answers. If you ask people for approximations, they will give you exactly what their calculator says. And they will give you things that it's just like, no, you can't answer that to that level of precision. I experienced this with a company I visited a few years ago when we were talking about this whole question of estimation and tracking against estimation. And I made a number of points, and the project manager then produced a Microsoft project plan and said, "You mean that this is not appropriate?" And I said, "No, that's not valid," because she pointed to this and she said, "Look, because currently on this particular task that we're doing, we're 52.5% done." I said, "Honestly, you're quoting that to 3 significant figures. It's based on an estimate of a thing that you have never done. to a level of accuracy or precision that you can't actually state. From an accuracy perspective, you're lucky if you're about half done. You're probably about a third done. But quoting it to 52.5 because the machine gave us the numbers, and we love to trust machines. So there is this idea that we end up doing this. We fool ourselves. And there's a number of metaphors and business practices that we find in business, but we also I find it in software architecture as well. People love the roadmap metaphor. I mean, even better, you can go online and ask for, roadmaps used to be quite dull, but now you can go online and just like, right, give me a PowerPoint template for roadmaps. I want to present something. And they all kind of look a little bit like this. They show a nice wiggly road. It's kind of like it's a nice graphic. And then you go and plug your text in there. Now, what's always bugged me about these things is that this is an almost entirely useless metaphor. It's so false. Because, why would I actually bother having a roadmap for a road that only has, if I only have one road? What's the point of that? That might give me distances, but honestly, I don't really need a map for that. This is where I live. That's a roadmap, okay? It's a mess. It's all over the place. It's highly evolved, but it also provides you with alternative routes. If there's a traffic jam here, go this way. Okay, there's other bits and pieces, 5 minutes quicker this way, 5 minutes. It's dynamic, it's evolving, it is highly, highly non-linear. And it has roads plural. If somebody shows you, the next time somebody shows you the project roadmap, the release roadmap, the architecture roadmap, put your hand up and ask them where the other roads are. What's the point of a roadmap with only one road? What I love, though, is when I was Googling around for this, I found this one of the templates. Right. Now, Phil, before we talk about this, Phil, the tube map for Baku, Azerbaijan only has one line. There, we need to show ordering. That is important. But there's also another signal that's being sent out. I remember going to a city when it only had one line many years ago, because what they're hoping for is they're signaling, here is the future. We only have one now, but guess what? There's more coming. There's an optimism built into that structure. Not the kind of, it's a cheery public works optimism, not this kind of like rather naive, we have constrained all the possibilities down to one. So there is a functional difference between these two. So what I love about this particular map is that, hey, here's an example template in PowerPoint for your roadmap. Okay, hands up, who had global pandemic messing up all of our projects in 2020? Nobody put that on their roadmap. This is the point. There was no process for finding out that would happen. Sure, we've been talking about, in fact, funnily enough, in January 2020, there was an article that I read saying we should expect a pandemic in the next decade. But nobody said it was going to start really kicking off, reaching a critical point of awareness in March. That even in January, I was traveling with a face mask. February last year, I was traveling with a face mask. It was just building. These things have a habit of doing that very, very suddenly. We could tell there was an inevitability about it. We had SARS in 2003. We had MERS. We had these. Something was going to happen, but nobody could say, "Oh, it's going to be 2020. It's going to be at this scale, and this is going to be the issue, and it's going to take this long to find a vaccine, and so on." Nobody was able to do that. You do not have a process for finding out what you do not know at this point until it is known. Now, why does this have relevance for us? Because it is about the future. It means that there are a number of practices that we adopt in business, but also when we frame things technically and we offer assurances that are actually beyond that are impossible for us to guarantee. There's a phrase that sometimes people like to use. They talk about, we're going to prioritize our requirements. Great, please prioritize them. But they talk about prioritize by business value. Now, business value is a bit of a fluffy term. It's not that it doesn't mean anything, it's just that it means many different things to different people. Business value, is that revenue? Is that value to my business, value to me, value to my team? Is it value to the customer? That's not the same as value to my business. So sometimes people kind of miss that. You're actually screwing the customer, but hey, your business is doing really well. Hi there, Facebook. So they're not one of the sponsors, are they? Okay, I don't think I'm going to get in trouble for that one. So the point there is business value doesn't have a precise meaning. It can have a meaning, but you have to say what it is. And when we say business value, do we mean short-term or long-term? Do we mean business value as evaluated over the next week, the next quarter, the next year, or the next decade? These will all give you different answers. They will prioritize different things. But that's not my quibble here. My quibble is not that the term cannot be defined well. It doesn't have a unique meaning. It means whatever you want it to mean, and you can tell people what you want it to mean. No, my quibble here is that you can't do it. And I don't mean, oh, I'm telling you you shouldn't. I'm telling you you can't, because it is, as far as we know, actually not possible within laws of physics as understood, unless you clearly step outside time. The thing you can't do is prioritize by business value. You can prioritize by estimated business value, but you cannot prioritize by business value, because until you arrive in the future at the point that you have said business value is to be assessed at, according to the meaning that you have said it will be assessed at, it is not possible to tell somebody what the business value will be. Now, you might be able to estimate it. In fact, I'm very sure that you can estimate it. But anybody who says, oh, Kevlin, you're just playing with words, really? If you don't know the difference between an actual and an estimate, maybe software development isn't for you. These are two fundamentally different concepts. The reason you cannot prioritize by business value is because physics. It's as simple as that. That's got to change the way that you approach these problems. Couch these things in humility, caution, and ranges, but also use the right words. Now, of course, I'm inviting people to change. So let's talk about Grace Hopper. She has a lot of things to say about change. Humans are allergic to it, for example. They love to say, we've always done it this way. I try to fight that. That's why I have a clock on my wall that runs counterclockwise. And that's why I have a clock on my wall that runs counterclockwise. I was thinking a few years ago, I suddenly thought, I live in the online shopping era. Surely somebody has created one of these. I stumbled across the Grace Hopper quote, not for the first time, but at that moment I suddenly thought, let's go and check out online. And yeah, this really messes with people. My kids, who can barely read an analog clock anyway, they come into the office, it's just like, what? I must confess, actually, after all these years, it started messing with me. When I look at another clock, I have to kind of recalibrate for a moment. But time can run backwards in that case. It's the only case that I know of. Now, let's get concrete. So anyway, you have excellent taste by having the same clock in your living room. Nice one. The minute we go outside a closed address space, what we can know changes. What is possible changes. Leslie Lamport's classic quote, his definition, very simple definition of a distributed system, is one in which the failure of a computer you didn't even know existed can render your own computer unusable. In fact, experienced this a couple of years ago with my publisher O'Reilly. There's fires in California, which are becoming a kind of a regular annual event worthy of news. Well, they're always an annual event. It's just now they're hitting the news an awful lot more. And we end up with this kind of consequence. And we've actually formalized. There is a concept here that we can talk about. Brewer's theorem, more commonly known as a CAP theorem. It was originally introduced by Eric Brewer as a conjecture, but it was actually proven to be a theorem. And a CAP is basically consistency, availability, and partition tolerance. Basically, properties within a distributed system. Consistency, basically the idea that if there is a piece of data, so this is all about data and our knowledge of value, if you like. Consistency is that every read will receive the most recent write, or it will receive an error. Okay? Availability. You will always receive a non-error response, but you won't have the guarantee necessarily that it's the most recent write. And partition tolerance is perhaps the least obvious of the terms. Consistency and availability translate relatively easily into an English description. Partition tolerance basically means if I have a network of a number of nodes, partitioning basically means, well, guess what? You have two networks. Rather than one, you have n networks. It partitions. There is something, a gateway perhaps, or a device or a machine just simply goes down. It's the idea that not all of the system can communicate with all of the rest of it. It partitions. Can we tolerate such partial failure? And there's another way of looking at it. A network is subject to partial failure, continuous partial failure. Technically speaking, the internet it doesn't work. It is always subject to partial failure. It's a not work rather than a network. But it is distributed, and it has appropriate partition tolerance. The thing is that with these three properties, we are given a limit. You can have two. You can't have all three. It's not possible. And people often talk about, well, I can have consistency and partition tolerance. In other words, oh yes, very well spotted, Hemel. Yes, Facebook had a little bit of an experience of this the other day. So the point here is we can have these two. We can basically, I can basically say, look, I can give you the latest value, or partition tolerance is we can continue operating. In other words, the system will continue functioning even when part of it is not working. Now, what I can offer you there is I can either say, you can have the latest value, or I'm going to give you an error. Okay, so I define some kind of staleness categorization, or I define an awareness that I do not have access to that value. Alternatively, I'll give you a different guarantee. I will always give you a value, but honestly, I can't tell you if it's the same one that everybody else has at the same time. I can't tell you if it's the latest. Now, some people have gotten to dismissing the last category. They've said, oh, consistency without partition tolerance isn't meaningful. They are incorrect, because this is what we experience when, when we reduce n to 1. This is actually useful. We can actually have consistency and availability, but no distribution failure tolerance when we are running in the same address space. This is achievable. But what we've effectively found here is kind of like a Heisenberg's uncertainty principle for anything that is distributed across space and time. So there is, hey, I promise you hitchhikers. What we have here is a rigidly defined area of doubt and uncertainty. There is an absolute boundary as to what is possible. It's not a technical problem. It is a problem that is woven into the fabric of what we know. Now, sometimes people use this kind of idea of things like eventual consistency and uncertainties about a system to say, well, we don't have to give people always the right results at a particular point. But I find this slightly frustrating, because you get it a lot with social media, but a number of other applications you can find on your phone, or you can look at a screen, and I've quite often had something that will tell me, whether it's something like a Tumblr or my my email inbox or something like that, and it will say, you have n items here, and then I look and there's n+1 items. And it quite clearly says across the top title bar there are n items, and yet when I count them down, it's n+1. And I've had people justify that by saying, oh, well, distributed systems, eventual consistency. No, we actually have a name for this phenomenon. It's called bad design. Sure, the state of a distributed system may not be in a consistent state, but this is in a client. It is the same address space. It is the same piece, it's the same body of code running. And you are on the same display, and one part says n and the other says n+1. That's just a failure to reconcile the two. There's no excuse for a client being wrong. A client is not inconsistent. It should be consistent with itself. It might not be consistent with the outside universe, but if you're going to show me n+1 items, the correct value to show in that title bar is n+1. It is not n. Okay, that is actually just not good coding. That is not a consequence of distributed programming. So there are some things you can't blame on that. So there is the last one, and we kind of, this is again is a boundary. It's even more specific, but it is one that I think is really important, because people use the term technical dent, they throw it around, and it's not even just that they're using the term in a way that it wasn't intended to use. They're also doing things with that number, just like we often do things with numbers that actually are not valid. So this idea, so for a lot of people, when they talk about technical debt, they actually mean unmanaged technical debt. There's a very big difference. For a lot of people, they assume technical debt is automatically a bad thing. Now, of course, we can have various comments about whether or not debt is a useful model for economics, but we cannot deny that certainly that it is there. But we have the concept of structured debts. We have the concept of well-calibrated debts. We have a concept of control and certainty and all of these various things. A mortgage is a structured debt in that sense. So I have a very interesting question from Phil, which I will come back to in a little bit at the end, which I realise I kind of let slipped by about 25 minutes ago. I was too busy looking at the chat. So the point here is technical debt. The problem is not whether or not you have technical debt. The problem is whether it is managed and recognised versus unmanaged and unrecognised. Many of us live our lives in various states of debt. A mortgage is an example of such a thing. If you have a mortgage, then hopefully you have a house to go with it. That was your benefit. That was your trade-off. You took a judgment call. You made a judgment call and you have a structured model of repayment. And so this is the point. This is the original metaphor. The idea was that we take on debt as a trade-off. But therefore, the implication is that you need to manage it. So if somebody says, oh, our code is riddled with technical debt, then they need to be more precise. They need to say it's unmanaged technical debt. If they say, oh my goodness, we have really loads of managed technical debt and we're on a path to fixing it, and our debt repayment model has been working for the last 5 years in our legacy system, then that's something worthy of praise. That's not a disadvantage. Obviously, you don't want to run up the meter carelessly, but there is a distinction here. But people use it to talk about the challenges, the deterioration of structure, which is related, of course. Deterioration of structure is running up a debt. It's a debt you're unaware of, and the meter is running without you being aware of what the rate is. And this observation, this goes back to 1980. Manny Lehman, wonderful paper, Programs, Life Cycles, and Laws of Software Evolution. As an evolving program is continually changed, its complexity, reflecting deteriorating structure, increases and less work is done to maintain or reduce it. Now, code bases were a lot smaller in 1980, and yet this is already an observed phenomenon. It was observed long before that in the 70s. But trying to reason about it, trying to communicate that is a challenge. And we've tried various things. People talk about code rot, code decay, software entropy, spaghetti code. People try various different metaphors, and they are, importantly, all metaphors. And technical debt happens to just be the most successful one. What characterises it is that, Ward originally came up with this in 1992. And interestingly enough, now Phil has just posted something that I'm really going to rail against in a moment. To do with quantification. So technical debt, it was already known in the 90s as a term. Ward Cunningham introduced it. He actually introduced it not to talk about these questions of software quality in general. He actually introduced it to talk very specifically to a finance company. He said, well, how will these people understand these trade-offs that I'm making? Well, they're a finance company, so let's talk money. And so that's why he used that. Had he been talking to somebody else, he would have used a different metaphor. What's funny is that this has become popularized partly due to Martin Fowler and others in the early 2000s. It became very, very popular, and the rest is history. But people have come to equate it with code that is bad. That's not to say, clearly code that is bad is technical debt. It's just that not all technical debt is necessarily a measure of poor programming or legacy issues. And as Martin said in the original, he's unfortunately updated the blog where he introduced this. And I say unfortunately because I think it was an important piece of history, and there's a little bit of revisionism there. But he says from the original, like a financial debt, the technical debt incurs interest payments, which come in the form of extra effort that we have to do in future development because of the quick and dirty design choice. And unfortunately, it turns out that part of the reason we tend to think of technical debt always negatively is because Martin emphasized all the way through the article, he used a phrasing, quick and dirty, quick and dirty. Now in English, quick and dirty, you're not saying something positive there. You're not saying this is a well-considered trade-off. You're all giving a value judgment that makes it strongly negative, and that's how people will perceive it. But the real issue that we need to come back to, that people keep overlooking, is it's a metaphor. That's the whole point. Metaphor is not identity. If it were identity, then we'd be using the exact words. Metaphor basically is a mapping, and it is by definition an incomplete mapping. We are saying, here is a thing that is difficult to understand. Here is another thing that is familiar, and which you already have a mental model for. What we're going to try and do is take the thing you don't understand and describe it in terms of a thing that you do understand. And this mapping will be imperfect, so please don't confuse the map and the territory, but it should give you the mental tools and the vocabulary to talk about it. That is the value of a metaphor. Sometimes people criticize the technical debt metaphor for not being exact. You can't criticize a metaphor for not being exact. That's the point. I mean, it can be better or worse, but you can't criticise it for not being 100% perfect. But it's a category error. If you make the mistake, like the sonar tools do, of quantifying it, and I'm not going to blame them, it's not just them, there are other people. People take the debt metaphor literally and numerically, and they put it, they have a currency value on a dashboard. This is our technical debt. Okay, and sometimes it is actually a currency value in like dollars or euros, and it's like, here is what we owe. It's like, no, you don't know that. You're just making numbers up. You know, that really is just, that's fiction. That's bad science. Call it what you will. That's not real. You don't know that. Okay, that's beyond the limits of what you can actually claim. You're using false precision, and you're using fabrication. You're using fiction, but you're passing it off as fact. You can't know that because you do not know actually what the cost of these things is. I also get people saying, well, you know, we've estimated the amount of time that, now I know that Phil's just kind of put in a point there. We don't actually call it tech. Sonar did. They did, and I've seen the paper. So as long as they move away from giving people the impression that they know what they're talking about. So these days, you know, do not map this idea. But again, I get other people saying, oh, but we've estimated our debt, but we don't measure it in currency. We've estimated it in hours. What they're doing is, that is not, first of all, that is not a debt. That is an estimate of debt. It is a debt in time. And that is a debt that is an estimate based on what does it cost to repay the debt. In other words, how long would it take us to fix that? That's not technical debt. Technical debt is not the cost of repaying the debt. Technical debt is the cost of owning the debt. That's the whole metaphor. The cost of owning the debt is not if I were to pay it off at this point. It is, you know, I wrote a piece about this one last year on the O'Reilly website on exactitude and technical debt. The message of technical debt, the technical debt metaphor, is it's not simply a measure of the specific work needed to repay the debt. It is the additional time and effort added to all the past, present, and future work that comes from having the debt in the first place. That is the metaphor. That is what it is trying to indicate. It is the accumulated cost and the cost going forward. That is a far harder thing. Now, if you do have an exact number for that, I mean, you're welcome to try that. I do recommend reading the piece. You'll find out that you're not in a position to do that. But there is an important point here. And again, it's like some of the earlier things. This is a limit of knowledge. It's beyond the knowledge that we actually have. So we have reached a countdown of 0. There's. I'm happy to take questions at this point within the within both the chat and the Q&A. There's and of course, you know, I'm not criticising technical debt as a metaphor. I'm criticising how people use it. I think it's actually not a bad metaphor. It's one of the more sustainable ones because it has a high level of mindshare and understanding. A lot of people understand debt, whereas it turns out that software entropy requires an understanding of entropy, and perhaps people are less familiar with that as a concept. Technical entropy, you see, you're on a loser to start with. Just people won't get that. I remember having to explain to somebody what entropy was when I once used the term software entropy and so on, and I related it to that, and I talked in terms of both the physics and information theory. And you know, that's how you know it's not a good metaphor, because if you have to explain the thing that's going to, explain the thing, then maybe you're at too many levels of indirection. The idea of using a metaphor is I take a thing that you struggle to understand, and I take a thing that you do understand, and I map one to this. If I have to explain the thing that I'm going to use to explain the thing, you get into a regress. So yeah, technical entropy, that's a loser, except with certain crowds. You might find yourself in a crowd who is au fait with entropy. In other words, it's an audience-related thing. If I have a room full of physicists, you know, entropy, absolutely brilliant. Just like Ward did with the finance thing. So there's this idea of, as Julian points out, the wording technical is a great communication tool when explaining the issue to non-technical people. We've seen things like the credit crunch, we've experienced all these things. It has a wide mind share. That's what its value is. But it is a metaphor. That's one of those key ideas there. Now, a couple of other observations. Anchor points out higher and right equating technical debt to pollution. Like pollution, technical debt is what you take away from the next generation. It manifests in reduced speed later on. That's great, except that's not the same as technical debt, because technical debt is sometimes you use debt to your advantage. Now, unless you're going to tell me that pollution is a really good thing, and I'm going to struggle with that one, pollution is based on the idea that is a metaphor or is a remapping of unmanaged technical debt, but it is not a mapping of managed technical debt. There is a subtle distinction there, which is important. That's not to say that pollution doesn't have any value when talking about certain elements in your code, but that it's not a substitute for technical debt. It might be a substitute for unmanaged technical debt, but it has a different. I actually quite like that. That's quite a good one. I often talk about signal to noise ratio in code, and pollution seems like they would sit very comfortably with that. But notice that these are not equivalent concepts. So there is a question from Phil. About just around half an hour ago, when I talked about the unknown knowns and the known unknowns are commutative. If something is a known unknown, then what I'm saying is I don't know. I don't know about it, but it is potentially knowable. The idea that the unknown knowns is, well, actually I shouldn't have said it's commutative. The unknown knowns is equivalent to the unknown unknowns. Sorry, that was my mistake, Phil. That was my slip up. Unknown knowns is equivalent to unknown unknowns, because those knowns are known to somebody, they're just not known to you. But the minute you say unknown, the prefix there is dominant. So yeah, thanks for asking the question, because it let me clarify what I said. I slipped up on that one, so my mistake there. Happy has a question. On topic in question, Kevlin, what do you consider to be the technical debt in C++, and how is the Standards Committee addressing it? Okay, the technical debt is massive. What, are we talking about the standard? Or are we talking about all of the code out there? Both are effectively true. Now, there is a system in place within the Standards Committee. The idea of cleaning up. Actually, if you regard a standard is a specification, therefore it's an information system. And therefore it is going to have some measure of debt within it, some of which is intentional, a lot of which is accumulated, much of which we can't really do much about and therefore have to deal with. So therefore it is known, or it is corralled. There is also the idea that there is a deprecation and removal model, so therefore there is a trimming model. There is a slight repayment model in that sense. So there's something going on there within the standard itself, although clearly, if you really wanted to do everything that you wanted to do, that would involve throwing most of the language out. There is still a small language in there, a small and elegant language struggling to get out. But if we talk about C++ worldwide and the billions upon billions of lines of code that are written there, then that constitutes a very, very large amount of unknown, unmanaged debt. And that is way beyond the scope of what the C++ Standards Committee would like to achieve. That's not really their remit. Discussions come up and they say, well, we don't want developers, if we give developers this, will this cause more problems, or will it let them simplify their code? Those considerations are always there, but nobody's actually setting out to solve this as a problem at the standards level. That's not never been considered the scope. And if it were, I think that would change things in a very, very fundamental way. Rebogo, so an eventual probability 0 is not always a theoretical impossibility. An event of probability 0 is not. Yeah, I guess there is a point there, but the important point there is that it's not a 0 probability event. There is a finite non-zero probability there, and Christopher clarifies another point. But the point here with bogo sort is we have no guarantee that a truly random bogo sort will ever terminate. And in fact, we're not even guaranteed that for an arbitrary, for a given, we can guarantee that for a given random number generator, whether or not it may terminate, is guaranteed to terminate. But for an arbitrary one, no, we're not either. So pseudo-random number generation, it's quite possible to cycle around a series of numbers and avoid the one that we need. So that is also a possibility. There is a point there, again, about communication, too many levels of indirection. Let me just scroll down. let's see. Okay, there's a few bits and pieces there. No, I think, Phil, sorry, I think you misinterpreted what I said. I disagree that the unknown unknowns equals the known knowns, because they qualify as two different bullets on my slide. The unknown unknowns are the unknown knowns. That's what I thought, if as long as your understanding mine are the same. No, the unknown unknowns are not the same as the known unknowns. So I disagree with that violently. So we're in agreement. No, the known unknowns is level 1, order 1. Unknown unknowns is order 2. Unknown knowns is also order 2, because the unknown takes precedent in that sense. So that's the distinction there. Okay, Ryan makes an observation. There is an elegant language trying to get out. Don't we already know that language is called Common Lisp? Oh, come on. You are kidding, right? Have you looked at Common Lisp? That is not an elegant language. It is a highly evolved language. My friend, if you want an elegant language, you need Lisp 1.5. Everything after that was a waste of time. Yeah, honestly, yeah, no. Common Lisp is a real dog's dinner. You know, I'm not claiming to be an expert in it, but I am claiming to have waded through the spec to find various things for a system that I did once work with that was indeed in Common Lisp. Yeah, the elegant language you're after is Lisp 1.5. So yeah. After that, you know, it all went downhill. Is there a level for unknowable unknowables? The unknowable unknowables is transcendent and beyond what we were talking about. So therefore, I guess the level probably for that is one of the things that we began the talk with, and is probably around here. So I don't know if that answers your question, Hussein. And Hemel, Smalltalk, yeah, Smalltalk is a footnote to Lisp. Alan Kay was deeply inspired by Smalltalk, and particularly the core equations. Yeah, somewhere I've got a Lisp book. Hang on. Here we go. The Lisp 1.5 Programmer's Manual. A very slim, elegant volume, really interesting. Kind of shows you how to implement a Lisp machine. This was published originally in '64, I think. No, 62. August 17, 62, and because you couldn't really have open source back in the day, because you know everybody's machine was different, the way that people went about it was here's how to build it, and it's actually quite a readable book for the early 60s. By the way, for those of you who don't want to spend however much this cost me, you can find a PDF of this online. I think it's a really interesting read if you're interested in programming languages and stuff like that. A particular page in there that is for Alan Kay. He said these are kind of Maxwell's equations for computer science. It's defining Lisp in terms of Lisp. There's a sort of homo-iconicity there. It's defined in terms of itself. Think cross-compilers and stuff like that. I remember the first time I encountered the idea that the C compiler is written in C. It's just like, what? How is this even possible? And then you realise, okay, yeah, there's an elegance of self-representation there, and then there's a little bootstrap moment. But that idea, that was what Alan Kay did with Smalltalk, as he generalised around that idea. And the original Smalltalk, he wrote out those Maxwell's equations in Smalltalk, for Smalltalk, in Smalltalk. What I love is, and not a lot of people know this, the original Smalltalk, Smalltalk 72, was implemented by translating this elegant Lisp into a onto a system that only had was a time-sharing computer system back in 1972. The original Smalltalk was written in BASIC. Okay, so maybe BASIC is the ultimate language. I'm not going to say one way or another, but that was one of those shocking revelations. So yes, opposite ends of the spectrum in terms of elegance. Any other... yes, Hemel makes a point about Alan Kay. There are only two pure arrow languages, Lisp and Smalltalk. Lisp has the concept of elegant closure through lambdas, although you need to go beyond Lisp 1.5 for that, actually, to be fair. There are some issues there that are solved in the 1970s. Lambdas actually in C++ are surprisingly powerful. They are actually like real lambdas. They are quite effective in that sense. Erlang is a very elegant model, and satisfies another one of Alan Kay's observations. which is that for him an object system is one that is about protection of state and is about dynamic binding and messaging. And Erlang actually fits that description actually really, really well. So yeah, that was a good one, Phil, to observe that. So any other questions? Any other questions related to any of the 6 impossible things or any of the possibilities I did not cover? I'm sure there are more impossible things. We're coming to the end of time. It turns out it does have a finite boundary. Who knew? Okay, I'm going to take that silence as no, Kevlin, we're done. Thank you very much. So hopefully I haven't messed with your brain too much. Hopefully that's given you some kind of thoughts, but also an appropriate humility, maybe a few things you can throw at your colleagues, project managers or whatever. Thank you very much, folks. And yeah, time for breakfast, if that is an appropriate time of day for you. I'm going to go grab myself a cup of coffee, and then I'm going to go and gather myself in Gathertown, and I may see some of you there. Thank you very much, everybody. That was awesome. Yeah, all day breakfast. Let's go for that one. Cheers.